Okay, so a few students have actually contacted me here recently and said something to the effect of, hey, I don't have a clue of what's going on in class. And that's okay. I'm glad you guys are reaching out to me. And so it's tonight I decided to kind of toss together a quick video that'll kind of sum up a little bit of what we've been talking about. Listen, I understand this distance learning thing is not an ideal situation for any of us, and we're doing the best that we can. I know you guys are working hard, and I feel for you seniors. We're going to try to make the best of a bad situation here. So hopefully I can make a little bit of sense here. There's nothing more that I would rather do than to be in 205 third period and walking you guys through this step by step in person, but unfortunately that's just not possible. So this is the best we can do. So we're going to talk a little bit about thermodynamics and heat energy today. So when we talk about heat energy, you have to understand that heat energy is just like every other type of energy, all right? Heat energy is measured in joules. It's a type of energy, just like kinetic energy or potential energy or anything else. Now, heat energy is different than temperature. Even though we kind of think of them the same way, they're not. Temperature is the measurement of the kinetic energy of the particles in a substance. So while they're definitely related, heat energy and temperature are not the same thing. We're familiar with the three temperature scales: Celsius, Fahrenheit, and Kelvin. Of course, in science, we're going to be using Celsius here in physics. So all of our problems are going to deal with Celsius. All right. So let's take a look here, and we have Celsius, Fahrenheit, and Kelvin as our temperature scales. Now, heat energy being measured in joules is not just a single thing. It's actually a mathematical function. And don't get scared when I say that. There's an equation here. Heat energy is the function of a substance's mass, something called its specific heat, and its change in temperature. Now, that begs the question, what the heck is specific heat? Specific heat is defined as the amount of energy that it takes to raise 1 gram of a substance by 1 degree Celsius. So however much energy it takes to raise 1 gram of whatever it is that you have by 1 degree Celsius. All right. Most of the time your specific heat is going to be a decimal number, point something. The one big glaring exception to that rule is water. Water has a specific heat of 4.184. And by the way, the unit for specific heat is in joules per gram degree Celsius. And you say, well, why the heck is it such a weird, clunky unit, joules per gram degree Celsius? Because when we look at the equation for heat energy, what we have is mass, there's your grams, change in temperature, there's your degree Celsius, and we want to end with joules. There's your joules. So that's why those units are all there together. The equation that we're talking about here for heat energy is this one. It is Q equals mc delta T. All right, where Q is our, to make this a little bit prettier here, where Q is our heat energy. That's your joules. All right. M is our mass. There's your grams. C is your specific heat, as we just talked about, which is in joules per gram degree Celsius. And delta T is your change in temperature. Now remember, change in temperature is always going to be the final minus the initial. Yeah, sometimes it's going to be, and that's in degrees Celsius, by the way. Sometimes that's going to be a negative number. Sometimes your initial temperature is going to be bigger than your final. That's okay. That's just indicating that your object lost heat. Don't flip those numbers around because you're afraid of getting a negative number. If you get a negative number, you get a negative number. It's supposed to be there, all right? It's always final minus initial, though. And really, that's the one big equation we have to deal with here, is Q equals mc delta T, where our heat energy equals our mass times our specific heat times our change in temperature. Now, how does this look in the real world? Let's put it to a problem and find out. So let's say we are asked to calculate the specific heat capacity of a new metal alloy if 15.4 gram sample absorbs 393 joules when it is heated from 0 to 37.6 degrees Celsius. Okay, cool. Like every other problem we have done all year long, write down what you know to begin with. Rewrite what the problem gives you. I don't care what order you write it in, just write it in. I see that I have a mass. I have a mass of 15.4 grams. And I'm going to think to myself, okay, is that the right unit? Yeah, grams, it is. Awesome. I see I have energy. Energy in the amount of 393 joules. How do I know that that's energy? Because of the unit. It tells me, joules. Joules is always energy. Is that the right unit? Yeah, it is. Now, I also see I have a 0 degrees Celsius and a 37.6 degrees Celsius. So there's my change in temperature. Now, my change in temp, again, is going to be final minus initial. Which one's my final and which one's my initial? The problem doesn't come right out and say it. But let me put on my English teacher hat for a minute. Let's use our context clues. Read the dang problem. What does it say? It's heated from 0 degrees, there's your initial, to 37.6, there's your final. So my final minus my initial, there's my final minus my initial. I'm not even going to break the calculator out for that math. It's going to be 37.6 degrees, and again, they're in Celsius. So I've got mass, I've got energy, I've got change in temperature. I'm looking for specific heat. All right, that's the number I'm looking for. Now, let's take a look at our equation again. We have Q equals mc delta T. Okay? So, let's plug and chug here and see if we can figure this out. My Q, that's my energy, that's going to be 393, is equal to my mass, 15.4, times my specific heat, which I don't know, times my change in temperature, which I was already figured out was 37.6. Cool. So, how do I figure this out? Well, the first thing I'm going to do is clean up this right side of the equation. I'm going to multiply 15.4 by 37.6. So let me pull up my calculator here. And I've got 15.4 times 37.6, and that's 579.04. So I have C times 579.04. Now, how do I solve for C? I divide both sides by that 579 number. And we should then get an answer that hopefully will be a decimal number. Let's see. Move this over here a bit, just so you can kind of see my math as I'm working through it here. So I'm going to take 393 and divide it by 579.04. 393 divided by 579.04. And I get, hey, what do you know, a decimal number. 0.67, we'll round out to 9. 0.679. So 0.679 is going to be the specific heat of this new alloy. And that, my friends, is our final answer. Boom, that's it. That's all we're looking for. All right? That's it. That's the beginning and end of specific heat. Now, we can go one step further and do one of the calculations like we did in class and in the lab with the calorimetry. So let's take a look now at a calorimetry problem. Okay, so let's take a look at this problem that's a little bit more complex, but using the same basic logic. So here we have a piece of metal weighing 59.047 grams. It's heated to 100 degrees Celsius and then put into 100 milliliters of water, which was initially at 23.7 degrees Celsius. The metal and water were allowed to come to an equilibrium temperature, determined to be 27.8 degrees Celsius. Assuming no heat was lost to the environment, calculate the specific heat of the metal. This is exactly what we did in lab, all right? And if you took chemistry last year, this is exactly what you did in chemistry last year. Same thing, all right? So we have that piece of metal. We had it in that boiling hot water in the beaker over the Bunsen burner. And then you quickly put it down into the cool water inside of the styrofoam coffee cup, put the lid on it, and measured and see how much the temperature of the water changed. That's all we did. That's exactly what this problem is showing. But here we have two different substances working. We have the metal and we have the water. All right? Again, first step, write down everything you know. All right? So what I'm going to do first of all is I'm going to write down what I know about the metal. All right? So the metal, I know I have a mass of 59.047 grams. The unit looks good. All right. Specific heat, I have not a clue. That's what I'm asked for, the specific heat of the metal. All right. Now, do I have Q for this? No, I don't. Well, that's going to be a problem too. Do I have change in temperature? Yeah, I think so. Let's take a look. So I've got, let's see here, was heated to 100 degrees Celsius and then put into the water, and they were allowed to come to equilibrium at this temperature. So the 100 degrees Celsius is going to be my initial temperature of the water, or of the metal. All right, we boiled it and then we put it in the cool water and let it cool off. What temperature was it when it cooled off? 27.8. So my change in temperature is going to be my final temperature, which is 27.8 minus my initial temperature of 100. All right. Remember I said a little while ago, it's okay if you're going to get a negative number here. And indeed, that's exactly what's going to happen. 27.8 minus 100. Yes, I know you've already done that in your head, but it's 72.2, and that's a negative. Keep that negative. That's important. Okay? Now, I think that's all I've got about the metal. Let's try about the water. All right. So do I have mass of the water? Well, I've got 100 milliliters. What does that do for us? Well, remember that in chemistry, 100 milliliters for every milliliter of water, what's the density of water? Well, it's 1, right? So every milliliter of water weighs 1 gram. So we can say that 100 milliliters of water is also 100 grams of water. Cool. So that's our mass, 100 grams. Do I know specific heat of water? Well, it's not given to us in the problem, but remember I said that's the one you kind of really sort of should know. That's 4.184. Q of the water, I don't know that one either. Change in temperature of the water. Let's see if I have enough to put together the change in temp. All right. So what was my final temperature of the water? Well, the water and the metal came to equilibrium at that 27.8. So my final temperature is also going to be 27.8 here. The water and the metal have the same final temperature. That's key. Now, what was my initial temperature of the water? Well, I'm told right here. It was initially at 23.7. All right, this is not going to be a negative number. So 27.8 minus 23.7, 4.1 degrees. And that's going to be a positive 4.1 degrees. All right. So how do we put these two things together? Well, it's this part right here. This assuming no heat lost to the environment part that is the key to this. We're assuming that all the heat that was contained within the metal gets transferred to the water and nothing is lost to the outside environment. Now we know good and well that that's not true, but it makes our lives and our math a lot easier when we make that assumption. So we're going to assume that all of the heat energy, all of the Q for the metal is going to equal all the water, or its Q. All right? So in other words, we're going to have the Q of the metal, and it's negative because it's being lost, equaling the Q of the water. I'll slide this guy over here. All right? So all the heat energy that the metal lost because it was hot and it was cooling down is going to get transferred into the water, because what happened to the water? It was cold and it warmed up. So now we can replace those Q's on either side of that equal sign with what Q really stands for, mc delta T. Now, do I have enough to solve for both sides of that equation? Well, let's find out. So I know with my metal, I'm going to scooch these guys over here a little bit more. With my metal, I'm going to have a negative, the mass of the metal. What was the mass of the metal? Oh yeah, that's right, 59.047. I'm going to multiply that guy by the C of the metal. I don't know that. And then I'm going to multiply it by the change in temperature of the metal, which is also a negative. It's negative 72.2. That's going to equal the mass of my water, which I said was 100, times specific heat of the water, which I already knew to be 4.184, times the change in temperature of the water, which I already said was 4.1. Now, when I plug all those numbers in, I notice something. First of all, the Q went away. We didn't have to have the Q for either the metal or the water. It didn't matter, because we had everything else that the Q is, mc delta T. And now that I've plugged in all of my numbers, I find that I'm only solving for one particular value. All right, this value right here, C, the specific heat of the metal. And that, my friends, is what the problem asked for. Do you see it? Now, once we're at this point, we can do the math. First step, I'm going to clean up this right side of this equation. So let me scooch my calculator over here so I can see my numbers. And I'm going to have 100 multiplied by 4.184 multiplied by 4.1. That should be a multiply. 1715.44. Cool. 1715.44. All right. Now, let's look at the other side of the equation. I have negative 59.047. Let me get this negative in here. 59.047. And I'm going to multiply it by this negative 72.2. And folks, what happens when I have a negative number multiplied by another negative number? The negatives go away. So we have 4263.19. So we have C times 4263.19. All right. So now that we've kind of cleaned up the math, can we solve for C? Well, yeah, we can. All I'm going to do is I'm going to take 1715.44 and divide it by the 4263.19. And I get 0.402 as C. 0.402. And oh, hey, remember what I said about specific heats? They should be decimal numbers. So my math here passes the eye test. All right? It's 0.402. That's the specific heat of the metal. Now we could go then to a chart of known specific heats of known metals, known values, and compare. All right? That's about as complex of a math problem as I can throw at you with this stuff. All right? Just understand that the Q that was lost by one thing, the metal, is equal to the Q that's gained by the other thing, gained by the water. That's the beginning and end of it there. All right, so the final thing that we'll talk about here are what we call the laws of thermodynamics. And we're only going to focus on two of them. There are more, but we're going to focus on the first two because they are the most important. All right, the laws of thermodynamics. The first law. The first law says that there's a relationship that exists between the heat energy of a system and how much work a system does. All right? That's all that the first law says. In mathematics, it looks like this. Delta U is equal to Q minus W. And you say, well, what's that supposed to mean? All right? So what this means is U is our internal energy of the system. Basically, all the energy that a system has internally itself. Q is our good old friend from the previous equation. It's heat energy. And then W is our work. In fact, it's work done by the system. So all you have to really understand here with the first law of thermodynamics is that it's a relationship between the heat energy of a system and how much work is done by that system. All right? So the whole energy of the system is equal to that difference. That's it. First law of thermodynamics. The second law of thermodynamics says this, that the universe is constantly becoming more random, more chaotic. The classic example is that your room, once you clean your bedroom, it will eventually become more messy, but it will never become more clean on itself. Like your room never cleans itself. That'd been awesome. I remember as a kid, that would have been awesome if that would have worked, but it doesn't, right? The house doesn't clean itself. Something has to be done to put it back into order. Left to nature, things become more random, more chaotic. This is called entropy. Entropy is the randomness, or the chaos in a system. All right, entropy always tends to slide towards more craziness. All right, right now there's a lot of entropy in the world. If you want to think about it like that. All right, back in January we were worried about I don't even know what, and now look at us. So things always tend to slide more to the end of more chaos. That's the second law of thermodynamics. You say, well, what does that have to do with heat? Well, it's the classic example of going from the ice in a cup of hot water. Let's say you just get a cup of water out of the tap and you put ice in it. What happens to the heat? Does the heat flow from the water into the ice, or does the coldness go from the ice out into the water? Well, by this point, you know the right answer is that the warmth, the heat, travels from the water into the ice. All right? And that's a little counterintuitive, I have to admit. But that's what happens. All right? Why is that? Well, think about the structure of the molecules. What does the structure of the warm water look like at the molecular level? How are those molecules acting? Well, they're moving around mildly fast. They're not in any specific structure, right? They're just kind of singing around there. What about the ice? What does it look like on the molecular level? Well, it's frozen. It's a solid. It's more crystalline shaped. It has a much more orderly pattern to it. So left to nature, what happens? That orderly pattern becomes more and more chaotic. What happens? The ice melts. Those molecules become farther and farther away from each other. They start moving faster and faster, and they lose that pattern, that shape, that crystalline structure. That's entropy. So there are your first two laws of thermodynamics. Now, the assignment from last week went into a little bit more depth with these. Go back and take a look at the assignments. Even if you did them and you turned them in, go ahead and go back and take a look at them again. Talking about calorimetry, talking about the heat energy, talking about the laws of thermodynamics. It's really important that you kind of grasp this. I posted that quick little video about the laws of thermodynamics by that guy on YouTube. I think Professor Dave was his name. But that was a pretty good clip. I think he really kind of encapsulated and explained it well there. Go back and watch that again, all right? If you have any questions, please let me know. I'm here for you guys. We'll tackle wave motion here at the end of this week and then after spring break. Hopefully we'll be able to tackle it together back in school, but we shall see on that. So again, if you have any questions, let me know. Good luck.